In the chapter on work and energy, we begin with this first section on the basic energy model. And in this section, we'll be learning about different forms of energy and how those forms are transformed from one form to another. We're going to talk about an isolated system and how the energy within that system relate to each other. And finally, we're going to begin talking about work and what kind of changes it makes to the energy of a system. From last chapter, we have seen how momentum is conserved when a system is isolated from its environment. In this section, we will see that energy is also conserved as long as the system is isolated from its environment. Energy will be abbreviated with the letter E. Now let's take a minute or two to review some of the forms of energy. Here we have a swinging wrecking ball. This is an example of kinetic energy, abbreviated K. Kinetic energy is energy of motion, and it will play an important part in the rest of this chapter. Next, we have a roller coaster car that is up on a hill. When objects have an energy based upon how high up they are, this is gravitational potential energy, and it's abbreviated U sub G. Gravitational potential energy is energy of position, and this is a type of stored energy. When you're at the top of the hill, you're not really doing anything, but you have the potential to do something if you were to suddenly fall. Another type of potential energy is that found in things such as springs and other elastic materials. In this picture, you see a young man pulling back on a bow, and this is elastic potential energy, abbreviated US. And that is just simply the energy found in springs and elastics, those kinds of things that when you either compress them or pull on them, they tend to spring back. And this is another type of stored energy. When you heat up a pot of water, you can tell that the water molecules are moving more rapidly. This is thermal energy, abbreviated E sub TH, and it is related to the total energy of the molecules. Thermal energy is studied in more detail in AP Physics 2. Both chemical energy, or the energy found in the chemical bonds of molecules, and nuclear energy, which involves the energy in an atom's nucleus, are not studied in AP Physics 1. So now we see that when we talk about the energy of an isolated system, we are talking about the total of all the different types of energies that might be existing within that system. An important property of energy is that it can transform from one form to another. Here we have 4 examples of energy transformations. For example, in the first one, the weightlifter is lifting a barbell over her head. This is an example of chemical energy from the food she's eaten being transformed into potential gravitational energy of the barbells because she's lifted it to a greater height. Now see if you can identify the other 3 transformations. In the second picture, the kinetic energy of the baseball runner is turned into thermal energy as he slides into second base. You can imagine the thermal energy if you were sliding with shorts on. You could definitely feel the heat from the friction. In the third picture, the chemical energy within the bonds of whatever is being burned is turned into thermal energy or heat. And finally, in the fourth picture, the elastic potential energy of the diving board transforms into kinetic energy as the diver is hurled up into the air, and that kinetic energy becomes gravitational potential energy as he reaches the top of his dive. Here we have the basic energy model, in which the energy of a system is represented by the total of all the different forms of energy within it, some of which may or may not be going through transformations. Keep in mind, this system must be isolated from the environment. However, sometimes energy can come into the system or leave the system, and this is done by primarily 2 forms. The first one is work. Work is the transfer of energy into a system by pushing or pulling on the system. The next section of this chapter deals with work. Another way that energy can come into or out of a system is through heat. Heat is the transfer of energy due to a difference in temperatures. This will be studied in AP Physics 2. Now keep in mind, these are energy transfers, not transformations. Transformations are the changing of one type of energy into another within an isolated system. Transfer is applying work or heat into a system or having work or heat leave a system, thereby changing the total energy of the system. Here are three examples of energy transfer. In the first one, the athlete is pushing on the shot put, and so that increases the kinetic energy of the shot put. In the second one, a match is pulled across a surface to ignite it. In that case, work is done on the match, which causes the thermal energy of the chemicals in the match to increase. And finally, a boy pulls back on a slingshot, thereby increasing the potential elastic energy in the slingshot. Because the only way to change the energy within an isolated system is to have either work or heat enter or leave the system, we can use this very simple equation that the change in energy of a system is equal to work. Now, by change in energy, we mean the change in any of the types of energy within the system, and it is this total energy that is equal to whatever work is done on the system or done by the system as work leaves it. This very simple equation can be stated as thus: the total energy of a system changes by the amount of work done on it. And this is known as the work-energy equation. It's a very important equation in physics and is one that you will use to solve many problems in this chapter. Let's return to our isolated system in which no work or heat is coming into or leaving the system. In this case, work equals 0. In such a situation, we can say that the total energy of an isolated system remains constant because there is nothing from the outside environment that can cause any changes. As important as the work-energy equation that we just saw was, the law of conservation of energy is even more important, and it will have important implications to solving many complex physics problems. Coming up in the next lesson, we look at work and what it means within the study of physics.